once we can do a linear fit, we want to be able to use this calibration curve and also understand the uncertainties in values we derive from the calibration curve and how to find those. So again, what we are doing here, just as a reminder, is in the calibration curve we have known concentrations. These are standard solutions that we've prepared usually along the x-axis, and we have our response of whatever sort it is along the y-axis. We measure a bunch of known points. They fall roughly along a line, and we do a least squares fit. That's not even close to a least squares fit, so let's do better. There we go, something like that. And the point of this is that we can measure an unknown that lies within this range. Maybe we measure a value, measure an unknown, get the response, and we can turn that response into a concentration. Say we measure a value that has a response here. We can go over to our least fit curve, our best fit least squares curve, our best fit curve, and find the known concentration that corresponds to that point. And that's the idea of how we use the calibration curve. Now, that concentration we get, we want to know what's the uncertainty in that concentration. And this is going to utilize the uncertainties in the slope and intercept, as well as the standard deviation in y. So the equation that we get for this is in your textbook. This is equation 4-27, and let me go ahead and write it out. So the uncertainty in an x value you get from a measured, right, this is from propagating uncertainty, is we'll get the standard deviation in y divided by the absolute value of the slope times the square root of 1 over k plus 1 over n plus the value of y that you measured minus the average value of y from the calibration squared divided by the slope squared times the sum of the x values from the calibration minus the average x value from the calibration squared. All right, let's break this down and also define what k and n are. Okay, so k here is the number of replicate measurements of the unknown. So say we do this experiment and we measure it 3 times and then average those values and put this in. K would be 3 in that case. Often this will just be 1, but sometimes you do get to measure it more than once. N here is the number of data points in the calibration curve. So in the example we have here that I've drawn here, we have 4 points, so that n would be 4. And again, let me just remind you y here. Let me use a different color. So y here, this is the measured response from the unknown. And y bar and x bar, these are the average values from the calibration points. So if you take each of those 4 data points that you have, average the x value, that would be x bar. If you take the average y value, that'd be y bar. And that's what goes into this calculation. Let's look at our example data and see how we can calculate this. So if we go back to the spreadsheet that we have here, let me just make this a little bit bigger. So this is all down here on this bottom half. This is how we calculate UX. So in this example, we imagine, imagine that these are, concentrations of 1, 2, 3, 4, and 6. And we get responses of 2, 3, 4, and 5. This is a little bit, silly because we have exact values. But anyway, we say we measure something at 2.72 is our measured value. if we kind of plot that along this curve here, we should get something at about 2.5. It looks like our actual value is 2.235. So our number of replicate measurements, we'll say we only measured it one time. We can change both of these and see how the rest of this changes. So then our derived x value, this is based on our equation of our line. So y equals mx plus b, we just solve for x. So we get y minus b divided by m, or b18 minus c10. So y minus b divided by m. So that's just going to give us the x value from the equation of our line. And then we want to find the standard uncertainty. And to do this, we have a bunch of other things we need to calculate. And so that's what is going on here in these cells here. We need these values. N is equal to 4, k is equal to 1 here, and we can see how this changes as we increase k. So n is equal to, however many data points we have in here. The mean value of y is we take the average of these 4 values. So that's written here using the average function in Excel. And then this is part of that fraction that we had. So this is the sum of x minus the mean value of x, which apparently we can use as deviation squared number here. All right. So we have these values here, and these are going to go into our standard uncertainty formula. And this shows what the formula is explicitly written out over here. So again, we have sy, that's C12 down here from our linest, divided by the absolute value of the slope, B10, times the square root of all of this stuff, right? So 1 over k, k is the number of replicate measurements here, plus 1 over n is our 4 data points that we had, plus y minus, so our measured y minus the average y, which is here, squared, b18 minus b15, divided by the slope squared, b10 squared, times this difference squared, right? The sum of the deviation squared. We put all that in, and we get that our uncertainty, our standard uncertainty in our derived x value is 0.37. So we would say that we get 2.2 plus or minus 0.4. We can then take this standard uncertainty and use a t-value to get a confidence interval. So this is not a confidence interval itself, but it's very easy to find a confidence interval from here. And so to find the confidence interval, we would multiply t, where t is n minus 2. It would be our degrees of freedom, and we pick the specific confidence level we want, 95% or whatever. So in this case, our degrees of freedom would be 2 because we had 4 data points in our linear fit. So that is how we use calibration curves. And we'll continue to look at examples of this in class, as well as you'll get practice with this for your homework. I will also post this Excel sheet on Moodle so that you will be able to use this yourself and look at it, manipulate this. You can change things and just also have these formulas for your own benefit later in the semester.